surface code, when people talk about surface code in relation to quantum computers, what are we talking about? Because it doesn't have seemingly a direct analogy in classical computing.
Yeah, it doesn't have, classical computers don't need to have that. So surface code is necessary because of the laws of quantum mechanics, right? So where does that come from? Surface code exists to correct for errors in qubits. So even very good qubits that only make one error every 1,000 operations, one error of every 1,000 operations sounds great, but when you're trying to operate at the same time millions of qubits, then you have to think that about 1,000 of them will have errors for every clock cycle. And then that becomes unsustainable. You cannot do anything useful with that. So what you need to do there then is perform error correction, which already exists in classical computers. Classical computers have error correction as well. The thing is, with classical computers, you have the classical physics, right, happening there. So you can check your bit and see if something went wrong and act on it, right? You can correct for it.
Right.
With qubits, you cannot do that because as soon as you measure a qubit, you collapse the wave function.
Right.
And you want to keep it alive for as long as possible. So the first trick you have to do is, okay, instead of looking at this wave function, I entangle together several qubits, say in my hand here 5. 5 is largely insufficient, but let's say 5. And instead of looking at the state of these 5 qubits altogether, that would kill my quantum information, I look at some relative, for instance, are they parallel to each other? They could be parallel all pointing up or all pointing down, right?
Right.
That's and still they would be parallel. And I'm not learning anything about the actual 0 or 1 that these 5 qubits are encoding together. So that's how we start doing error correction. How do we move from that to surface code? This is all great, but you're still asking if they're parallel up or parallel down, right? And in quantum mechanics, you have another principle that most folks have heard of, which is the uncertainty principle, right? You usually hear about if you know your speed, you don't know your position. If you know your position, you don't know your speed. There's an equivalent of that for spins and for qubits in general, which is if you know what's happening in the vertical direction, you lose all information about the horizontal direction, right? About this qubit. So you need to protect them both independently, and that's where the surface code comes from. So instead of just repeating my information in one direction, I need to repeat it in 2 dimensions, in 2 directions, right? So that's the surface code. It's repeating the same information that normally would be in 1 qubit across many qubits in both horizontal and vertical directions. And now what is my logical qubit, meaning the qubit that is protected against error, is a tile of, say, 30 by 30 qubits.
Right.
Or 100 by 100 qubits. And how big this tile is depends on how good your qubits were in the first place.
And it's so interesting how all of that's interrelated. So the architecture that we've got at Diraq, how does it relate and how does it improve on the surface code ramifications of eventually calculations done with those qubits? Is that a fair question?
Yeah, it is a fair question. So a few things. One is, it depends on how good your qubits will tell you how big the size of this tile is. And if you do the math, it's a little bit scary because really, even if all you need is 100 qubits on the side, right?
Yes.
100 times 100 is already 10,000. So that's 10,000 to encode one logical qubit.
Right.
So you need numbers. You need very, very large numbers.
Very nice. And so they're cheap, easy options that other brands, they're not going to get. So we do need the millions of qubits to get the loaded. And you can't escape that reality.
Exactly. And all the connections need to be at this level of quality. So you cannot afford to have weak links between separate chips and things like that, right? So that's the first big difficulty that spin qubits solve. They're small enough. They're well integrated with classical electronics to quickly act on errors, find where errors happen and solve them. So that's one big advantage.